Hello and welcome to High Voltage Engineering. We are continuing with the generation of high voltage and currents. So in this class we'll be talking about generation of impulse voltages. So you have to first understand what are impulses. Impulses are the high values at a small time interval. Okay, the impulse can be an impulse force, it can be an impulse current, impulse voltage, whatever the values will be a very high value of high magnitude, but the the time taken for that high value to reach is very small. So this is called an impulse. Okay, so we'll be talking about generation of impulses. Now, why this impulse generation is required? Because again, for the testing of the apparatus, these impulses are required to test the apparatus for the lightning protection. Okay, so we'll talk about the standard impulse wave shapes. Okay, then we'll talk about theoretical representation of impulse waves. Then we'll continue with the circuit for producing impulse waves. So we'll be talking about a couple of circuits that produce impulse wave. Then we'll talk about a very famous impulse generators called the Marx circuit. Okay, and the components of a multi-stage impulse generator. We'll talk about that. Then generation of switching surges. So standard impulse wave shape. So on the right hand side you can get the standard impulse wave shape. So you can have you can see the wave starts rising and reaches a point. The point is marked as 100. So it is since it is the wave is terms in terms of percentage magnitude. So at 100% it reaches the peak and slowly it dies down. So this is a typical wave. Okay, so the transient overvoltage due to lightning and switching surges cause steep buildup of voltage on transmission line and other electrical apparatus. Impulse waves are specified by defining the rise of the front time, fall or the tail time to 50% peak value, and the value of the peak voltage. Okay, so first you need to understand that the transient over voltage, why do we require this impulse voltage? Because impulse voltage are there in the in our transmission line where there are transient over voltage due to lightning or any kind of switching that occurs. They have this impulse voltage present in our transmission line. Now, how is the impulse voltage defined? It is defined as the rise of the front time. The rise of front time is nothing but the time it takes to rise, and the maximum value, and defined by the fall of the pulse to at least 50% of the maximum. So how do we define an impulse? We need three parts: time for the impulse to take a rise, maximum value, and the time of fall to 50% of the maximum value. So when the impulse wave shapes are recorded, the initial portion of the wave may not be clearly defined or sometimes may be missing. Moreover, due to disturbances in certain superimposed oscillations in the rising portion, hence the front and the tail have to be redefined. So why is this definition? Let's say the impulse wave has no current a proper shape. Like we have an AC power which have a sinusoidal shape, a DC power which is a straight constant shape, or you can have a triangular waveform, any kind of waveform, but impulse has no particular shape. So in order to identify one impulse and differentiate that impulse to the other impulse, we need to give different different names to the impulse, and this differentiation is done by one, that is its maximum value. And not only the maximum value is important, how fast it rises and how slow the thing falls. So three components are required, but sometimes the rise of the impulse is not found. Okay, it is so fast. So again, this rise and fall again you have to be redefined to understand the quality of the impulse. Now this is the portion of the text taken from the book. Okay, so this describes the impulse wave. The points corresponding to 10% and 90% of the peak value are located in the front portion, point C and D. So you check the point C and point D. So it is 10% to 90%. The line joining the point extended to cut the time axis at O1. So if you join C and D, it will cut the time axis at the point O1. O1 is taken as a virtual origin. Okay, so we are actually defining an impulse here. Now 1.5 times the interval between T1 and T2. You check T1 and T2. T1 is the time the impulse is at 10%. T2 is time the impulse is at 90%. Okay, so the 1 point times the interval between time T1 and T2 corresponding to point C and D is defined as the front time. Okay, so what is front time? It is 1.25 into the distance of T2 minus T1. The point E is located at the point E. Point E is at the 50% level. So the point E is located on the wave tail corresponding to 50% of the peak value, and its projection on the line is T4. So O1 T4 is defined as the fall or the tail time. Got it? In case the point C is not clear, okay, or missing from the wave shape record, the point corresponding to 30% of the peak value F is taken, and its projection is located on the time axis. So when we do not have this C, we can take C is 10%, but we sometimes the impulse is very fast. We cannot record the 10% of the impulse wave. So we will take the 30% and then make that to be the origin. The wave front time is that in that case was defined as 1.67, okay, into that distance. The tolerance that can be allowed in the front and the tail time are respectively 30% and 20%. So we can have an error of 30% for the rise and the tail time, which is 20%. The Indian standard specification is defined as 1.2 divided by 50 microsecond to be the standard lightning impulse. The tolerance allowed in the peak value is 3%. So this impulse, if you want to know what is the impulse, it is nothing but a lightning strike. It is an impulse, so it happens so fast. Okay, and within that time, we need to understand what kind of impulse is that. How one impulse is different from the other, because no two impulse will have the same rise time and same fall time and same peak value. Now, theoretical representation of the impulse wave. The impulse wave, whatever is the impulse wave, that can be defined as it's a constant multiplied by a difference of 2 exponential. Okay, so that is given in this term. So it is basically defined as V naught into exponential minus alpha t minus exponential minus beta t. This is the alpha and beta would be different for different impulses, but the basic equation of the impulse is nothing but this. So the V naught in the equation represents the factor that depends on the peak value. That is no, because depending on the V naught, you will get different peak value, because exponential the maximum it can so it's a negative, so basically it will go the maximum it will go to minus 1. Sorry, 1 for individual exponential. Okay, so V naught is nothing but the peak value. Okay, so these are the different waveform and the different alpha and beta and V naught been given. Okay, so you can understand how these waveform, the impulses are named. So this naming can be done in terms of alpha and beta and V naught. So circuits that produce impulse wave. So impulse wave circuits are nothing but a RLC circuit. A double exponential waveform can be produced in the laboratory with combination of the series RLC circuit over a damped condition for the combination of two RC circuits. So there are these 3 or 4 type of circuits. Okay, so the first the circuits are almost all circuits are similar, only a mild change in the circuits. So I want all of you to at least go and try to solve the circuit. The circuit is being solved in the book. I have given the PDF. It's rather that you go and solve it by yourself. One circuit if you can solve the other also. So from the first circuit you can have the solution given on the right hand side. Okay, so it is nothing but what you do is that you form the differential equation, then you go to the Laplace transform, and you arrange the output, which is the output across the for the first circuit, which is across R. Okay, so in the Laplace transform, and you do an inverse Laplace. Okay, so the equation for the first circuit is given on the right side, and for the circuit B and C it is given on the down. Okay, so these are the different values of the circuits. The only thing is that the exponentials will be different. Okay, so the alpha and beta for every circuit would be different. This is what is the equation is all about. Okay, so this is the end of the lecture. Thank you.